I think that this topic, which is something that I've been thinking about for a long time, is more closely related to possible changes in field theory, and so it might well fit into that vision of physics, or what vision you come to, and it also continues in a natural way from what I was starting to say yesterday. So, as you see, this is described here as a discrete viewpoint about physics that's related to non-commutativity, gauge theory, and differential geometry. And I begin from a place that I mentioned yesterday about thinking about discrete measurements. So this is actually a description of what we actually do when we measure, but with a little constraint. I'm thinking of a series of times at which some measurement is made, one after another. So far, that's realistic. And that there is some delta t, that dt is not necessarily infinitesimal, and that one can measure a velocity from the positions, if those are positions, or one can measure a derivative if those are things whose differences can be taken, by taking next time minus previous time divided by the change in time. And then, if we make an observation, I will write it as that symbol for the observation. And then to the left of it is a next time observation. So the order of observation goes from right to left on the page. That's the symbolic convention. So if I were to observe velocity and then observe position, I can think about what will happen when I do that. Or if I observe position and then I observe velocity, I can think about what will happen when I do that. And now you will notice that the time series is going on. So at the very least, and this is written in the form of what we would write down at the very least, if I observe velocity and then I observe position, then the position that I'm observing is over here at the next time. So if I would observe velocity first and then I observe position, I get the next time position in the formula of the product of those two. On the other hand, if I observe position and then I observe velocity, I get the first time version of the position. And so position and velocity don't commute. And this shows that position and velocity don't commute for a simple reason of sequencing of observations in this world of discrete measurement, and has nothing yet to do with quantum mechanics. But there is a commutator, and let's compute it. So if I compute the commutator, I take the difference between this one and that one, and you see I get another x prime minus x. I get x prime times this, and x times that. I get x prime minus x squared divided by dt. So the basic commutator of position and velocity is that position velocity commutator is equal to the change in x squared divided by the change in time. We'll come back to that in a moment. Even sooner. If I think of setting the commutator equal to a constant, then the constant would be the change in x squared divided by the change in time. And I'm thinking of the new x is equal to x plus or minus the change in x. This is a discrete analog of Heisenberg's equation, diffusion. It's the diffusion constant, if it's set equal to a constant. And it comes usually for different motivations, which I hope I have a slide to show you how you get to the diffusion constant, just to remind us all where it usually comes from. But it's remarkable that that by just starting with discrete observation and thinking carefully and writing down what happens to the non-commutativity of it, that you arrive at the diffusion constant, and you arrive at a certain level of description of Brownian law. So physics is coming out very rapidly.
Just a quick question: What would x double prime minus x prime represent?
Well, that would be 2 time steps away.
Okay.
Right.
Okay, so
Yeah.
that's related. All your x
That's all.
primes are related.
So
to
I
your
might
prime.
work out a second derivative in time by looking at 2 time steps, right?
Okay.
Yeah. It's all very concrete here.
But you're going to focus on the x prime minus x.
Well, x prime minus x is the derivative, right? Where the derivative is obtained by getting as close as you can to the next time, right? If you're doing a continuous derivative, getting as close as you can means getting infinitesimally close. Another comment, if you include infinitesimals in your work, as most people who think in applied mathematical terms do, then you're also thinking discretely at the same time as you're thinking continuously, because you've stepped by a recognizable symbolic step dx. And you think about those dx's as small amounts. So, in a certain sense, when one thinks in terms of infinitesimals, one is thinking in terms of increments or finite difference calculus. But then something is usually ignored. You just say, oh, I take the limit, and I forget about the non-commutativity that's inherent in the situation. Here I want to keep it in. And also, I want to think of this as abstractly as possible, if necessary. That is, x might not be a location. It could be an entire object in some category, if you like. It could be just the whole scene. Everything, whatever it is that's being observed. It doesn't have to be a single number. You can think of it as abstract. There would still have to be a notion of difference. And that notion of difference would be however the distinction was measured. And there would have to be a product, and I don't know what that would be in the most general case. But you can think of it as much more general than just numbers. And they might not commute, among other things. These x's and x primes, they might not commute. What would I do now?
Get rid of that. I don't know how that disappeared.
I like that slide.
No mistakes.
Shows our understanding.
It was down to 0. The Adobe Reader is having a problem. It's like hit your back. Hold on, let me try this. We hit the back button.
It was reading in
You
fine.
see, it was reading in fine. Let me try something before they could use the control. I'll just try one thing. See, that's where we get the error on that slide. See, I can go to this slide, but I'm getting the error on the next one.
Looks like, let's see, something wrong with the reading of that. Can we get beyond it? Well, I'll tell you what, it'll only take a moment, and I'll just hook up my own computer with the same document.
You download.
I think we'll forget about this. I'll just click it this way. Okay. Here's the next slide, finally.
Yes.
Okay, so now, one thing that would be useful, you see, is when we made that calculation, you see, what did I do? I said, well, I would evaluate by allowing that a derivative causes the time to the left of it to shift by 1, right? If I were to evaluate the derivative, then there's no indicator in the algebra that tells you that you should have shifted the time, and so you could get confused. So we would like to make it a part of the algebra itself that the time shifts. This is going to add a little non-commutative algebra into the situation. And it's what I did, without saying all this, to get to the square root of -1 yesterday. Well, oh, thank you, but it's too many things to hold, of course. Yeah, I can try. To get to the square root of -1 yesterday, we added a temporally sensitive element into the algebra. Here I haven't put it in yet, so I could do these calculations without it by just remembering that this is temporally sensitive, and whenever I evaluate it, I have to shift everybody to the left. But that means if there was more to the left, all of that would get shifted as well. So a stratagem to deal with that is to have an extra symbol J, which has the property that when you shift it past something, it causes it to shift up in time. In other words, J inverse Xj is equal to the next time value of X. That's a time shifting operator. And then we can define X dot to be J times X prime minus X over dt. And then you see the time shifting element is still in the language even after this has been evaluated numerically. And then everything will work the same as before, except that you would push a J all the way out to the end. And then you see something interesting happening if I do that. Not just that it will keep your calculations from going wrong, but that since Jx prime is equal to Xj, I can rewrite this as Xj minus Jx. And so the derivative itself is written as a commutator. The derivative x dot is written as the commutator of x with j divided by dt. That's really a discrete derivative, and it's written as a commutator. Commutators satisfy the Leibniz rule. The Leibniz rule is just basic calculus that you would like to have around. You want to be able to say that the derivative of a product is equal to the derivative of the first multiplied by the second plus the first multiplied by the derivative of the second. Commutators always satisfy that rule, and so we have the following way of dealing with discrete calculus via non-commutative calculus. I've written it out again just to show you the formalism of it. If f tilde is f of x plus h, and I'm thinking of derivatives like f of x plus h minus f of x divided by h, then there's the derivative, there's a discrete derivative, f of x plus h minus f of x divided by h. F tilde minus f divided by h. Then the derivative of f times g, if you work it out, is the derivative of f plus f tilde times the derivative of g. F gets shifted up by a little bit. That's literally what happens if you work out the discrete derivative. There's a little shift in there, temporal shift if you like, of h's sign. And that h is going to 0 in the usual situation, and so you get the usual Leibniz rule. But if the h isn't 0, then it's there and shifted. If we introduce this shift operator and redefine the derivative by multiplying by the shift operator, then you get that the Leibniz rule works, and you get that the derivative is given by a commutator. So this changes your point of view about calculus and about representing things entirely in some way. You can say that instead of working in ordinary calculus, I will work in discrete calculus, and I will think of my models as being discrete. I still have then, with this extra non-commutative idea, I still have all the usual rules of the calculus. But all derivatives are represented by commutators. Every derivative in sight is represented by taking the commutator with somebody. Okay? So I believe this is simply summarizing what I just said. And here's what it looks like if you were going to compute it, just for fun. Xx dot, okay. So that's x times j, the time shifted, times x prime minus x over the time difference. And then the j shifts over to the left, and you get the x prime. On the other hand, if you do x dot x, the j is already on the left, and you get the other expression. So you see how the time shifter language is doing automatically what you were doing conceptually a moment before, thinking, well, this must shift the time. And here's the diffusion constant coming up again. I think I already said this, so we'll let it go for now. And I will come back to the diffusion constant in a later slide and remind you where it comes from normally But let's look at where we are now if we generalize everything that we've said. We're saying that we're working in a field of, in a new field of derivatives where I'm actually in some possibly non-commutative algebra where I can define derivatives by taking a fixed element and looking at the commutator with that element. All right? So that gives me a derivative. That's my derivative. It satisfies the Leibniz rule. It is a derivative in the direction n, if you like. But there is no notion of direction here yet. This is very abstract. I just have a non-commutative algebra, linear algebra, so I can take differences. And I have many, many derivatives. And these derivatives don't commute with one another either because it's very non-commutative. So we're already in the situation that one usually waits a while to get to of covariant differentiation and curvature. Because covariant derivatives are defined from ordinary derivatives by shifting an ordinary derivative by something, and then the derivatives no longer commute with one another. You no longer have d by dxi commutes with d by dxj. D by dxi is one of these. It's a derivative in some direction. So we can start the framework of the advanced calculus by assuming that we are in this kind of which way did I do it? Back C1 and back B1, and cycle like that, and add them up. You get 0. I'm sure you've seen this before, but if you haven't, you should mark down on a piece of paper and write out each of those and add them up. Hey, we'll go to 0 for you. All right? Just a fundamental thing about the beginnings of the subject of realgebras, if you want to go there. Now, if you take derivations, that is, a collection of so-called derivatives, things that satisfy the Leibniz rule, each one represented by some element in the algebra, so that the I-directional derivative is given by the commutator Reden sub I. You take a bunch of them. Then you can define the curvature of the collection to be the collection of commutators Ni and J. I want to convince you that that's the right notion of curvature by reminding you that curvature in differential geometry is in fact given by taking covariant derivatives in two different directions and taking the commutator of them. That corresponds to parallel translate in the I direction, parallel translate in the J direction, and take the difference from parallel translating in the J direction and then parallel translating in the I direction in classical differential geometry. And so that commutator of derivatives is the IJ component of curvature. But what you will find if you compute it here, because these are represented by commutators of n sub I, what happens is that if you compute this on an F, you will find it is the commutator of Ni and J with F. So that the commutator of the representatives represents the curvature represented by the commutator of the individual elements. So we have curvature. Before anything else, we have curvature. And we have the derivative. Oops, I went backwards, sorry. Oh, here's the proof. Might be interesting to look at the proof. If I take delta I of delta J of F, then you see I'm taking delta I of delta J of F. And it's right for applying the Jacobi identity, right? There's a triplet for the Jacobi identity, and it's equal to minus the sum of the other two terms in the Jacobi identity. And then this one here can be flipped around from its minus sign by flipping these two. And this one can be flipped around from its minus sign by flipping these two. And then what am I looking at? I am looking at the Ni-Nj part, and I'm looking at differentiating with respect to I first and then with respect to J. So you see that the difference between delta I delta J and delta J delta I is given by the commutator, as I said. This formula follows. Everything followed here by using the Jacobi identity, and in fact in this framework everything is just an expression of the Jacobi identity, which makes it a very interesting arena to work in. Things that you thought were fundamental or maybe particularly important all turn out to be the Jacobi identity. So I'm going to show you an example of the so-called Bianchi identity about the curvature. Here is our derivative with respect to the A direction, and I've written it in one of the ways that one writes such things. Colon A is delta A of F, is F taking the commutator with ends of A. So I have this curvature here. And here's the Jacobi identity for three instances of differentiation, A and B and cycle. And that, now read it off. And this says RAB differentiated in the C direction plus RCA differentiated in the B direction plus RBC differentiated in the A direction is equal to 0. If you open your book on differential geometry and look up some identities about curvature, you will realize that that's the so-called Bianchi identity. Many identities that are important about curvature are all coming from this underlying fact of the Jacobi identity. So this is a way to think about calculus and differential geometry. And I have a tendency to go backwards sometimes. All right, so now let's see what a general framework for this looks like. We might want to start with coordinates that look like ordinary advanced calculus. So I have a bunch of coordinates which are commuting with one another. Now remember, we're in this very general situation. These are no longer numbers or even vectors of numbers. They are elements in this abstract algebra, but of course they could be represented as vectors of numbers. And these guys commute with one another, so they form a local situation which is looking like an ordinary coordinate patch. And then I'm going to have pi representing the I partial derivative of f with respect to xi. So that means that I'm going to have them commute with one another. I'm trying to make a locally commutative situation. So these guys commute with one another, and then I'm going to assume that di of xj is equal to delta ij. Yeah, where that means 1 when I equals j, 0 otherwise. So I assume that the commutator of xi with pj is equal to delta ij. That says the derivative in the j direction of xi is equal to 1 when they're equal and 0 when they're not. So that's the derivative in the I direction. And I have set this up in such a way that it's quite symmetrical with respect to j and xi. So you can also define the derivative with respect to pi to be equal to the commutator of xi with f, putting it on the other side. So that then we're saying that the derivative of pj with respect to xi is equal to delta ij. The same thing, only it's on the other side now. So we have this dualized version where I have these, which you might think are momenta, but if they are, they're very abstract momenta. And I have this set of commutator equations, which looks familiar, but it's not meant to be anything other than what it is. And we have these dual derivatives. But I want to do physics with this, so I should have time. And I will import time in the most abstract way that is fitting with this. That is, time derivative of f should be the commutator of f with somebody. So with malice aforethought, I called it h. And so we have that the temporal derivative of anybody is equal to the commutator with h, or h is another element in our algebra. Of course, that comes from Hamiltonian mechanics, the idea of it. But here, if you were a very abstract inventor of non-commutative calculus, you would come upon this as a natural definition. And notice that in quantum mechanics there should be an I, and I'm not actually going to discuss quantum mechanics here. I'm just sticking with this framework. But now it's rather interesting to realize that Hamilton's equations are simply a consequence of what I have just set up. Take dpi dt. That's the commutator of pi with h, by definition. Remember, h, we might as well call it the Hamiltonian. Taking the commutator with the Hamiltonian gives you the time derivative. But that's minus hpi, and hpi is the derivative of h with respect to xi. So we have dpi dt is minus the h dxi. On the other hand, look at dxi dt. That's a commutator of xi with h, which is by definition dh dpi by our duality. And those are Hamilton's equations. Hamilton's equations without any physics, because no physics has been put in here other than the notion of having a time derivative. And the notion of having a time derivative is just the notion of having some extra derivative, right, so far. In order to get physics in, you have to decide on what is the Hamiltonian. All the physics would be in the Hamiltonian. But Hamilton's equations are a mathematical part of this beginning. So you see this beginning by starting with the notion of discrete differentiation and discrete observation, and then representing everything by discrete derivatives, but representing the discrete derivatives by commutators takes you into a world where certain aspects that you normally thought of as frameworks for mathematical physics are in fact part of the mathematical framework. They're just there. Hamilton's equations are just there. I think I have a slide to remind us where Hamilton's equations usually come from. Yes, if you were thinking in terms of classical mechanics, the momentum is mdq dt, where q is the position, and the Hamiltonian, the energy is p squared over 2m plus some potential energy. And Newton's law says that mv squared q dt squared is equal to minus dv dq. And then if you take the h dp, you get p over m, which is equal to dq dt by definition, right? And on the other hand, the h dq is equal to dv dq and gives you minus the dt. And so that's where they come from originally. And there is physics in there, and what looks like very particular physics. So you may think when you're going down through this that it somehow depends on the quadratic Hamiltonian, but on the other hand, from our point of view, it's just part of the framework. You're ending up in part of the framework. I'll stick this. No, I won't. I remind you that if you compute f dot and you have Hamiltonians, I'm in classical calculus now. If I compute f dot, I get the f dt, which is the f q dot plus the f dt p dot. But your q dot is the h dp, and p dot is minus the h dq. And so Hamilton realized that he had a kind of commutator here, the Poisson bracket. And this is the Poisson bracket of f and h. And so he could write f dot is equal to the Poisson bracket of f and h. And there is the beginnings of Hamiltonian mechanics. And the Poisson bracket satisfies the Jacobi identity, acts like a commutator. And it was Dirac's insight that if you replace Poisson brackets by commutators, you made a transition that formally looked like the transition to quantum mechanics. Here we started with commutators, and we aren't in classical calculus, but we're doing something like Dirac's transition nonetheless, and finding out that there are interrelationships between classical physics and the world of the commutators. This is an interesting point. I'll just slow down for it. If you look at a Poisson bracket, it doesn't obey the Leibniz rule. If you were to just take it for what it is, if you take the derivative of the Poisson bracket, you will get the derivative of the first, and you get the derivative of the second, you get an extra term. And it will obey the Leibniz rule if this expression is equal to 0. But that, in fact, is an integrability condition for Maxwell, for Hamilton's equations. So we're back at Hamilton's equations again, and how Hamilton, in the usual situation, it's Hamilton's equations that are making things work on the nose in ways that we imported into our framework from the beginning. Then I also wanted to mention about diffusion. You see, the usual way you think about diffusion and arrive at the diffusion constant is quite different in principle from what we started with. You say you have a Brownian walk, x at t time tau, t plus tau, is x at time t plus or minus some increment, Brownian walk. And let's suppose that it's equally probable to go to the left or to go to the right. And then you decide, well, I think I'd like to calculate the probability. I'd like to find out what is the probability of being at x at time t plus tau. Well, you could have come from x minus delta or x plus delta with equal probability. So there's the recursive formula for you in relation to time. So this is a discrete time formula, but it isn't quite in the same framework. But it is really close in essence to thinking about the thing discretely. And then, if you look at this formula and rewrite it a little bit, you end up with the diffusion equation. That is, if you were to write the left-hand side and make it into a difference quotient for the partial of p with respect to t plus tau of t divided by tau, then the right-hand side becomes this. I had to subtract off a p of xt, so I got subtracted off here. But I've doubled it and 2 here, so that this equation is exactly correct. And I've divided by delta squared here, h squared. That should be a delta squared, sorry. So this is correct. I just divided by 2 and added 2 to keep track of the 2's that were already there. All right? So this implies this. But this is a second difference. This is the expression for the second partial of x with respect to, of p with respect to x. So you see that if we translate these into derivatives, it says dp dt is some constant times d squared b dx squared. And the constant is the square of, as I said, that should have been that's the spatial difference. But I somehow called it h without calling it h before. It's delta. Yeah, right, it's delta. So that's the delta, we cancel the delta squared, pardon me. So we have space step squared divided by 2 happens to be divided by 2 would be a constant. If that would be a constant, then we could take the limit and take this over to a differential equation. And that's the usual way in which you arrive at the diffusion equation describing a Brownian process. But you see you get the square of the space step divided by the time step by a somewhat more complicated probability argument this time and a continuous differential equation. But they both fit together, the commutator version of the Brownian one and this one. So that was a return to what we were saying earlier. And then space squared divided by time, if you look at it in terms of Planck's mass, length, and time, the Planck mass, the Planck length, and the Planck time, if you look at that, you find out that Planck length squared divided by time is h bar over Planck mass. So if you're thinking of comparing the diffusion equation with Schrodinger's equation, then that's where the comparison point works. That you can replace this by 1/2 of h bar over m, and so you end up with h bar over m as the coefficient, and then the diffusion equation looks just like Schrodinger's equation except for an I. But now let's go back to our general framework. I want to think about the most general equations of motion in this theory. That would mean that I would be looking at the original coordinates xi, and I would have some law. dxi dt is equal to g sub I, where g sub I are some elements in the algebra. That would be an equation of motion. And in order to see what that would be like, we'll write the equation of motion, this is a kind of momentum, as the very simple momentum that was representing dx dt in the original framework, shifted by an a sub I. Now I'm using the usual kind of formalism so you can compare it in your mind. This is just saying it's shifted by somebody, that it's arbitrary, but I've written it in relation to the pi. But of course you can think of the ai as corresponding to a potential, as in an electromagnetic field potential. And then we want to think about the curvature of the situation with regard to derivatives in the GI directions. Well, let's work it out. GI, commutator GI, is PI minus AI, PJ minus AI. Work out the commutator, you get PI AJ minus the J AI plus the commutator of AI AJ. This is the well-known formula for the curvature in differential geometry, and in particular for the curvature of a gauge field, if you were interpreting this as a gauge field. So again, the point to notice here is the economy by which these things are popping up. These are things that you usually think of as being told much later in the story, but they're popping up immediately out of just the framework of representing advanced calculus in terms of non-commutativity and commutatives. And that means that this can be interrelated with electromagnetism if you want to, by putting in the gauge field for electromagnetism, or it can be interrelated with Yang-Mills theory if you wanted to use other AIs or gauge theories. Then there's a matter of method, because I'm aiming at showing you how differential geometry is coming out. So suppose that I have some elements Gij which commute with the xk's and are symmetric. And suppose that I chose my H to be in this form. All right? That's a non-commutative version of the usual Hamiltonian, quadratic Hamiltonian. If you were thinking, for example, of writing the Hamiltonian as Lagrange did on an arbitrary curved surface in three-dimensional space and using its metric. And then you can calculate that the xi xj dot is equal to the gij. I've even included the calculation, but you don't want to look at that. But this is the basics of thinking about the structure of a quadratic Hamiltonian in this situation, and what happens to the xi xj dot. It looks like the metric. So we have an expression for the metric here, and in fact, if you look at the calculation, you'll see that both things are fitting together. That is, from advanced calculus, you would expect this equation, right? In advanced calculus, you would expect that the derivative of f in time would be the time derivative, would be the space derivative of f, d by dxi, times xi dot, plus the space derivative, and I've written it on both sides in this case, summed over I, symmetrized it. That's a natural way of matching what you would expect in advanced calculus, and this actually is equal to the time derivative. This essentially only happens for quadratic Hamiltonians. And so if you ask this non-commutative world to match with the ordinary world of advanced calculus and standard physics, you find that it demands a quadratic Hamiltonian, and so it looks like ordinary physics. So you could say, where do quadratic Hamiltonians come from? And you could take as a peculiar philosophical answer, well, it follows from the principle of matching in constraint the non-commutative world and the ordinary world of advanced calculus. That's a curious thing to investigate, and is something that Tony Deacon has been investigating for a long time. The idea of constraints of that kind giving rise to different aspects of classical physics via non-commutativity, including certain versions of Einstein's equations, which I won't go into. In fact, we're almost done here. Let me see. I wanted to show you this one because I had a lot of fun discovering it, and it's quite amusing. You might remember the Levi-Civita connection written in lower indices. It is that you take the metric and you get a connection. And it's the right one in standard differential geometry. The Levi-Civita connection is the one where when you parallel translate using that connection, you preserve angles, right? It's the one that gives you Riemannian geometry. but here, we're doing this in this very rarefied situation. Here's our method. And I claim that, if we let gamma ijk be equal to di gjk plus dj gik minus dk gij, and that's the usual formula for the Levi-Civita connection, then you will find equal to k is equal to two derivatives down from the acceleration form for x k double dot. Now, if you think about that for a moment, you realize, well, that's good. That actually is exactly what would happen if we were in classical differential geometry, the physical differential geometry, and we were looking at a geodesic. Because if we were working with the Levi-Civita connection in a geodesic, and we looked at the form for the acceleration and differentiated it off to momenta from it, we would end up with just the connection itself, because that's the form of the form of equation for a geodesic. So here, this is picking that up, and it's picking it up just by the Jacobi identity. This is nothing but a Jacobi identity rewritten. Let me show you, and we'll stop with this one. We could go on for a long time showing various kinds of correspondences. Gjk dot, well, here's gjk. So if you take its dot, it means you get a dot on one of these or a double dot on the other one. All right. Now let's look at what happens if I take out of xk dot, dj out of xk double dot. Pi hat means take the commutator with xi, and then take the commutator with xj. So first with xj, then with xi. Then this guy here, xj xk double dot, is equal to the metric dot minus this commutator of xj dot with xk dot. Okay, and then this adds up like that. This with this, and this with that. And now this guy here, we can apply the Jacobi identity to that and cycle it around. It's got a minus sign, so these get plus signs. K goes over, and then J goes over. There you are. Now you look at this and read out what you've got. And by shifting derivative to the other side, you get that you can put the dot on the xi and put a minus sign here. Over here, I have xk dot and xi xj dot, and the same thing here. I just copied it. All I did was change that. And now I'm going to read them. That's all. This one is delta I of gjk, because just a minute. I lost a minus sign, so. Oh no, I forgot to tell you something. That I'm going to take delta I to be the minus the to be equal to the commutator with xi dot, not with p. All right. These are the covariant derivatives that are involved in the situation. So the xi dot is the analog of the pi. But I'm going to define delta I to be commutator with xi dot. Sorry, I should have told you that before. It kind of spoils the joke to have to tell it to you here. But then this is delta I of that, and these are both minus, and there's the formula for the Levi-Civita connection. So this actually goes further, and you get that the acceleration in this general form is given in this form. This is what I meant by saying that it looks like it's moving in a geodesic. And then there's an extra term, and that would correspond to a field, and that would correspond to moving in an electromagnetic field if the AI was the usual potential for an electromagnetic field. So this situation embraces a large amount of physics in a different formalism, and gives some insights that you wouldn't have considered if you were staying in the usual formalism. And the thing to remember is that everything I've said could be interpreted as discrete physics, even though we're going on and playing with it as though it wasn't. So there's this very rich framework, which might well interface with many things, and hopefully it will interface with some of the things we talk about later today. I think this is a good place to stop. So I'll stop. Yeah.
Professor Kauffman, it's another demonstration of the unreasonable properties of mathematics.
Right. The unusual coincidence of mathematics with physics and our ideas. Yeah. I'm sorry, couldn't hear.
Why unusual? Unreasonable.
Yeah.
Unreasonable.
I think it's exactly the opposite.
That's unreasonable.
Unusual, but not unreasonable.
Well, mathematics is really the formal abstract study of logical, self-consistent relationships.
Yeah.
The real world works. Therefore, it can't be the real world, not the one we're civilizing. It works. It can't be inconsistent by itself or consistent.
Right. But remember
So
that.
we're studying the real world if you
Yeah.
study mathematics in an abstract sense.
But I like to
It
think
can't be
that.
otherwise.
Yeah, I like to think that what's going on here is that we started with a little more care about observation,
Yeah.
and we got this very close-fitting situation that looks surprising, but maybe it's not so surprising since we actually are talking that it fits with a lot of physics,
Yeah.
because we are paying a little more attention to what it means to observe. It doesn't mean that you can derive the observed world from just the mathematics. Some of the features of what we think of as being part of our description of external reality are actually features of how we make mathematics that works well with regard to observation. Lots of things in the external world are just given to us, like the Hamiltonians, or the potentials for the electromagnetic field, and all those things. It's not, you wouldn't have a chance at all to derive the external world by trying to do this sort of thing. But that you would notice that there are a lot of coincidences is a good thing.
Einstein said exactly the opposite. He said if you observe the real world, you'll never guess the right answer. You got to think it through first, and then maybe you'll come on as insight. And the only way you can think it through is with mathematics. Something we call mathematics. There's some social aspects to it.
That's because he never did an experiment.
And he got some answers anyway. He didn't say the experimentalist got the right answer.
The connection between this and exponential EIT, that's what transports you from one to another.
Oh, that's right. Yeah, I mean, in physics, one often writes e to the I something about the Hamiltonian to write the time evolution operator.
Yeah,
So that J can be fitted with a good deal more structure if you want to.
It makes the mathematics simple.
Yeah, right.
That's just the extension of that, right? In computer series, I think comes out the right term.
I don't want to do more slideshow, but one of the reasons I put up the Bianchi identity is because when you are thinking about general relativity, then it's the Bianchi identity that is the key thing to understanding why Einstein's tensor has divergence 0. And that's one of the great examples of mathematics fitting the physics, right? The fact that you could find this curvature tensor with a combination of curvature tensors which has divergence 0, so you could match it with.
Another interesting point is the non-quadratic Hamiltonian. It seems to me, I'm calling this post-point, get away from quadratic. As soon as you get away from quadratic, you really run into problems.
Yep. Yep.
And nothing fits, and no conservation laws go out the window, and Gauss's law goes out the window. In other words, everything goes to hell.
Yeah.
I think there's one point which is very good reason to be very careful about mathematics. These are Maxwell's equations. Maxwell's equations are mathematically very beautiful.
Yes.
And they have the symmetry from electric and magnetic appearances. But that's not the physics behind it. Physics is extremely different. As we know, mathematics is a very, very small side effect of the magnetism. Very small side effect of the electric field, a relativistic side effect. So in a similar way as the Coriolis force is a side effect of Newton's law of motion. Yeah? So to make this, to have this mathematical instrument of the symmetry of the Maxwell's equations, that gives us an understanding that we have here the electric effects, and there are the magnetics, and they are connected in some way. But the physics behind. But many people think it because many physicists think it because they look to the equations and get this impression. But this impression is completely wrong.
So what is the point you're making? Certainly Maxwell's equations give us a unification of the electric and magnetic fields.
Yeah, but that's, it sounds mathematically that this is something symmetric or something equivalent. But from the physics, it's not. We know that what we call magnetism is in fact magnetic forces are in fact electric forces. But they look in a specific way because we have some relativistic effects like contraction and so on.
Oh, yeah.
And we have this delay by the limitation of the speed of light. And this gives us the impression that there is a magnetic force. But we know, which also was mentioned by Einstein, that if we are in a magnetic field and we measure a magnetic force, we can move in a certain way and the magnetic force disappears. And that's something that shows us that it's like Coriolis force. And nobody would try to build a specific theory of the Coriolis force. It's not necessary. We know Newton and that's enough. But we have, for instance, this famous three-dimensional potential, magnetic potential. Would we have some specific potential for the Coriolis force? Nobody would think we need this because Newton covers everything of it. And the electric force also together with relativity of course, covers everything which concerns magnetism. And this is, I say this to say, look, if we look to the mathematics of the Maxwell equations, it's seducing us to have a wrong impression of what the physics is.
Well, I think an example of that is it took a long time for people to realize that the potential had real influence, right? Around effect and things like that are not visible if you're just thinking in terms of Maxwell's equations.
Mm-hmm. There are things which are also an error from Maxwell's equations that follow that an accelerated charge will radiate, emit energy. Mm-hmm. And I think this is wrong, and it's a very bad conclusion, which is generally taken, but not true.
Let's continue our discussions in the hallway to Lou.